Our lesson 6.7 is about simple machines. If you are new to this channel, please do not forget to subscribe, hit the bell, and do some comments. I post educational videos at least twice a week. So let's get started. Our lesson 6.7 has the following goals: to identify the 6 types of simple machines and their uses, to solve problems involving the mechanical advantage and efficiency of a simple machine. What is a simple machine? A simple machine is any device that changes either the force applied or the distance moved when work is being done. Simple machines are tools used to make work easier. You have probably used some simple machines but did not realize that they were actually called simple machines. All machines are combinations or modifications of 6 fundamental types of machines called simple machines. These 6 simple machines are the lever, pulley, inclined plane, well and axle, wedge, and screw. Number 1, the lever. The lever is a stiff bar that moves about a fixed point or the fulcrum. A lever is used to pull, push, or lift things. A pulley is a simple machine that is made up of a wheel and a rope wrapped around it. Pulleys can be used to lift heavy objects by changing the direction or amount of the force. An inclined plane is a simple machine. It is a flat surface that is higher on one end. You can use this machine to move an object to a lower or higher place. Inclined planes make the work of moving things easier. You would need less energy and force to move objects with an inclined plane. These pictures show some examples of inclined planes. Number 4, the well and axle is another simple machine. The axle is a rod that goes through the wheel. This lets the wheel turn. It is easy to move things from place to place with wheels and axles. These pictures show some examples of wheel and axle. Number 5, a wedge. A wedge is a simple machine used to push 2 objects apart. A wedge is made up of 2 inclined planes. These planes meet and form a sharp edge. This edge can split things apart. Some examples of wedges. Number 6, a screw is a simple machine that is made from another simple machine. It is actually an inclined plane that winds around itself. A screw has ridges and is not smooth like a nail. Some screws are used to lower and raise things. They are also used to hold objects together. Some examples of screws are shown in these figures. Listed below are terms commonly used when describing simple machines. These terms have the same definition for all types of simple machines. On the input side, we have effort force, which is given the symbol F sub E equals the force applied to the machine, usually by you. The effort distance, or D sub E, is the distance over which the effort force is applied, how far you push or pull. Work in, which is given the symbol W sub IN, is the amount of work that is applied to the machine, where Wn equals F sub E times D sub E. F sub E is the effort force in newtons, D sub E is the effort distance in meters, and W sub N equals the work in Newton meters or joules. On the output side, we have resistance force F sub R equals the weight of the object being lifted. Resistance distance D sub R equals the distance that the object being lifted is moved. Work out, W sub out, equals the amount of work done by the machine. The formula is W out equals F sub R times D sub R, where F sub R equals the resistance force in newtons, D sub R is the resistance distance in meters, and W sub out equals work out in Newton meters or joules. In addition to the terms defined on the preceding page, there are three common measurements used to describe simple machines. These terms are defined and discussed below. The mechanical advantage of a machine is a number that is used to represent how much a machine increases the force that is applied to it. The number for the mechanical advantage is a factor that you can multiply by the effort force in order to determine the output force from this machine. It is common to look at the mechanical advantage from two perspectives. One, what is the actual mechanical advantage, AMA, of the machine in the real world? Number two, what would be the ideal mechanical advantage, or IMA, if the machine had no friction? The actual mechanical advantage of a machine is defined to be the resistance force divided by the effort force. In symbols, AMA equals F sub R over F sub E, where F sub R is the resistance force in newtons, F sub E is the effort force, and AMA, which is a unitless because it is a ratio of two like quantities, is the actual mechanical advantage. The ideal mechanical advantage of a machine is defined to be the effort distance divided by the resistance distance. IMA equals D sub E over D sub R, where D sub E is the effort distance in meters, D sub R is the resistance distance in meters, and IMA equals the ideal mechanical advantage, which is unitless. It is also common to look at the efficiency of a machine, or how much work you get out compared to how much work was input. The efficiency is given as a percentage. The efficiency can be calculated in two ways. Efficiency equals work out over work in times 100%. Or efficiency can also be calculated using the formula efficiency equals AMA divided by IMA times 100 and then add a percent sign. Example number 1. A force of 100 newtons is applied to a simple machine In order to lift a box that weighs 300 newtons, the effort force is applied over a distance of 4 meters, causing the box to rise 1 meter. Determine the following. Letter A, effort force. F sub A equals 100 newtons, which is given. This is the force that is applied to the simple machine. Letter B, the effort distance is also given to be 4 meters. Letter C, the resistance force. Resistance force is usually the load or the weight is given to be 300 newtons. Letter D, the resistance distance is given to be 1 meter. The work in equals F sub E times D sub E equals 100 times 4 equals 400 joules. Letter F, the workout equals F sub R times D sub R is 300 times 1 equals 300 joules. The actual mechanical advantage is F sub R over F sub E equals 300 over 100 equals 3. The ideal mechanical advantage equals D sub E over D sub R equals 4 over 1, which is 4. The efficiency is workout over work in times 100 and then percent, which is 300 over 400 times 100%, which is 75%, or the other formula is efficiency equals AMA over IMA times 100%, and you get the same answer, which is 75%. Example number 2. 45 joules of work is input to a lever that provides 30 joules of work out. The effort force is 15 newtons and the resistance force is 30 newtons. Determine the following. Letter A, work input or work in equals 45 joules. It's given. Letter B, work out. It's also given to be 30 joules. Letter C, the effort force is given again to be 15 newtons. And letter D, the resistance force is 30 newtons, which is also given. Letter E, effort distance. From the formula, W sub n equals FA times D sub E, and solving for D sub E, we get D sub E equals W sub in over F sub E. Substituting the values, we get 45 divided by 15 equals 3 meters. The resistance distance. From the formula, W out equals F sub R times D sub R, and solving for D sub R equals W out over F sub R equals 30 over 30, which is 1 meter. Letter G, AMA. The actual mechanical advantage equals F sub R over F sub E equals 30 over 15 equals 2. Letter H, the ideal mechanical advantage is D sub E over D sub R is 3 over 1, which is equal to 3. Efficiency is work out over work in times 100% is 67%, or the other formula is efficiency equals AMA over IMA times 100%, which is 67%. Example number 3. A 75% efficient machine is used to lift a 60 kilogram mass. The machine has an ideal mechanical advantage of 4. What is the actual mechanical advantage of this machine? From the formula, Efficiency equals AMA over IMA. Solving for AMA, we get actual mechanical advantage equals efficiency times IMA. Substituting the values, efficiency is converted to decimals, which is 0.75, and the IMA is given to be 4. So, multiplying these two values, 0.75 times 4 equals 3. How much effort force is required to lift the mass? From the formula, AMA equals FR over FE, and solving for the effort force F sub E, we have F sub E equals FR over AMA, where FR is the load in newtons. Since it is given to be in mass, kilograms, then we multiply the mass and the acceleration due to gravity to get the value in newtons. So 60 times 9.8 equals 588 newtons, and the AMA, as we have already solved, equals 3. Therefore, substituting the values, then simplifying, we have the effort force equals F sub R over AMA is 588 over 3 equals 196 newtons. Thanks for watching. Please do not forget to subscribe.